This is the planning section of the design coursework. It's the first section. It's worth 6 marks and has 5 parts. Description of the problem, analysis of the problem, and specification, which is the last one, are all pretty much the same as you've already seen in the assembly coursework. The part 3, the theoretical or online research, is new, as is the practical investigation or in-person research. It's got 2 bullet points in the mark scheme. If you were to attain, say, a tick here and a tick here, then that would be effectively all of these being ticked. So you would get 5 out of 6. So each point in the design coursework is worth a mark, which is slightly different and slightly easier when you are marking it or when you are trying to work out how you're going to get on. So each bullet point has a higher weighting, it's worth an entire mark. Identify a problem to be solved, and well, that's fine. That's the first bit, description of problem and analysis of problem. Detailed relevant research is the bit that we're going to talk about. That's the new bit. Design spec, qualitative and quantitative, as normal. Notice it's now 4 of each, so it's slightly more, and 3 or more detailed realistic electronic parameters with tolerances where applicable. Previously, it was only 2. So slightly more expected of your design specification, but only really an extension of what you've already done. So description of the problem. Describe the problem your client is having. Do not go into detail about what it will do. So the description of the problem should be what the problem is. Don't muddle up with what your circuit does. Make sure that you're going to solve everything in the problem that you describe. So you are describing the problem, but don't start describing billions of problems. Stick to one thing and solve it. Make sure that everything in your circuit is something in the problem. So make sure that it all feels applicable to the problem at hand. Your circuit hasn't got lots of extra bells and whistles that doesn't really seem appropriate. So if you're designing a circuit for a blind person and possibly someone helping them, then it would be fairly reasonable for it to include LEDs for the helper. However, if it's just for a blind person and it's got LEDs, obviously that's useless functionality. So make sure that your problem is clear. Analysis. This should be explaining in detail how your circuit is going to solve the problem. It does need to be clear and coherent. It should be noticeably longer than it was on the assembly coursework. And you should be covering as if you are explaining the block diagram of your whole circuit. It is a very sensible thing at this point in time to be trying to create the block diagram. The block diagram is only needed for the realization section, so for section 3, but it's a very good idea to be doing it now in the planning so that you can kind of see what's going on and it'll help you write this analysis. The online research. This is new. This needs to be relevant to your coursework. You need to do 2 pieces of online research and 2 pieces of investigation, practical investigation. You simply go online and look up the pinout of some of the chips you're going to use, and you copy and paste them and explain how that was useful. That's it. Do make sure that you explain how the research has helped you. So in other words, it should be explaining that you now know how to wire up the chip. There's 4 gates within the IC, something like that. Now, online research does not have to be the pinout of a chip. But if you want to do something else, it needs to be relevant to the circuit that you built. So if you do lots of research about how the internal workings of a NAND gate, that's not really useful. You're not going to use that. You're not going to build a NAND gate from scratch. So that's kind of pointless. It's not going to get you any marks. It's not relevant. So make sure if you're going to do something that's not a pinout, it's really, really relevant to what you're going to do. And this is possible. So you could be researching distances for cars, in terms of parking them, and different distances and different frequencies and this kind of thing. So it's possible, but very tricky. It's much easier just to Google a pinout that you're going to have to look up anyway. So here's an example. There are 4 sets of exemplars. Please do peruse them, do look at them, and they will help you. Just something to note, you're not allowed to do the 555. So the 555 is not allowed. The reason for this is that you should already know the layout for a 555 astable and 555 monostable, because that was part of the year 1 course, and that's something that you should know off by heart. So you're not going to get any marks for looking up something you should know. But it could be an op amp, or it could be a logic gate. Those are not things that you're expected to have memorized. Notice that the person here has explained what they Googled. The URL should always be included, so they've noted where it comes from. Here's a nice big pinout, and they've explained at the bottom what this actually does. So it tells them it holds 2. They share the same voltage. They haven't actually stated that they'll now know how to wire up, which is like usually the main thing that you gain from this, and the thing that I would normally just write without thinking. So this shouldn't take you more than 5 minutes. Don't make it long. Half a page is absolutely fine. Practical investigation will take you a little bit longer. Again, you need 2 of them, and this is best done with input or output components, not things in the middle. You can do it with processing chips. It's a lot more fiddly and a lot easier not to, particularly as most processing chips are covered as part of the course, so you can't do a practical investigation about how an AND gate works because you should already know that. You are testing it to work out how it works. Now, there will be some things that you already know how they work, such as the push to make button. That doesn't mean you can't research them. It's not technically part of the syllabus, so it could be something that you have worked out. Do look at the exemplars for some good examples of things. You cannot copy them, but you can go, oh yeah, I'm using that. I could research that. Oh, that's a nice way of laying things out. I'll borrow that idea and I'll go and do my own research. That's absolutely fine. Make sure that your test plan, results, and analysis are clear. It should be clear that you've planned how you're going to test it, that you've then got some results, and you've analysed it. Again, make sure it's clear how you're going to use the research. It shouldn't just go nowhere. The common mistake for the practical investigation and the online research is that students do them, forget about them, change the circuit, and no longer use that logic gate or that particular input component. If so, you need to go back and change this. It's not relevant if you haven't used it. This is an example. It's a pretty decent example. You can see at the top, they've explained how they've done the test. So this is the test plan. This is their results. They've done a really good thing. They put it into a graph. So this is, more part of the results, really. The only thing is this line of best that's absolute crap. It should be a curve, and there are ways of making curves. So do try and make it actually fit the data. This last statement is all right. It's not very good. They kind of get away with it because the rest of it before then has been decent. But this last bit is pretty rubbish. Why is this important? How does this link to the circuit? So link to your circuit. Why on earth have you bothered to do it? So if I'm being critical, it's not great. It's pretty good. They had a good idea, just bad finish. So do link it to your circuit. Specification. This is exactly the same as for the assembly coursework, but it requires 4 quantitative points and 4 qualitative points instead of 3 of each. And it requires 3 realistic measurable parameters, which all of your quantitative points should be anyway, so this isn't really a big ask. It should be the function of the whole circuit, not a part of it. So it shouldn't be, my circuit is going to have 3 LEDs, because guess what? We can see them. That's not really saying anything. It should be when the on button is triggered, the LED the red LED flashes for 30 seconds. In fact, that's really 2 points. So when the button is pressed, the LED starts to flash. Point 2, the LED flashes for 30 seconds, plus or minus 3 seconds. Notice I state the tolerance to ensure that it's got the attention of the user. I've explained why I picked the numerical value, so do make sure that you explain it. Everything should be testable. Everything should be what you're going to test in the realization later on. This is an example. They have split it up into qualitative and quantitative as two separate sections. I personally wouldn't do this. I think it's a little bit confusing because it's much easier just to talk through a whole circuit. But for some students, qualitative and quantitative kind of get a little bit muddled. So if you're that person, do put them as separate sections if it makes your life easier. You should be explaining why you picked the particular values. This is okay, it kind of gets away with it, but do make sure that you're really clear why you picked any numerical values. And that is it.